Hi everyone. My name is Yilei. I'm Associate Teaching Professor at Syracuse University. I'm also the Civil Engineering Program Director. The first author is Kate Chemnitz, who is my former research assistant and now studying civil engineering in Lehigh University. I have two undergraduate research assistants, and then one is currently studying engineering management at the University of Michigan, who's supported by the source. The other is Kate, supported by the WISE, and also Steel-like and Sika provided material properties. Okay, a little bit of background. So this is a typical bridge bent and comprised of a column piers and a pier cap on the footing. So this topic is on the column itself. So I will present the background, the problem definition, and how to address the problem by proposing new configurations, and what does this new configurations is incorporating, what type of different materials, and how do we analyze or simulate this type of configuration by using OpenSees. And once the simulation was calibrated and shows a promising applications, then we will the parametric study was conducted in addition to the ground motion simulation and provide some conclusions. Okay, so here are the problem, right? We see a lot of corrosions in the infrastructure, especially in Northeast, in this area, and also in Midwest, where the winter operations is critical for de-icing applications, and that will introduce the chloride to a corroded, to cracked reinforced concrete, and also in the marine applications due to the chloride intrusion by the seawater. And this can be seen from the top. This is from a typical marine application for a concrete pier corrosion, and also to the bottom is the one that I took in Toronto, Ontario this July, and this is in downtown. When you're passing through the Yonge Street towards the waterfront, you're passing through the Lakeshore Boulevard, and it looks like they have already identified a huge problems over here. The rebars were corroded, and they already took out from the concrete spot, but the rebars were exposed, but it was not repaired yet. So I was looking forward to next time when I come back to see Toronto and to see how they repair it. But nonetheless, the reinforced concrete structures, or in the bridge structure, comprise of 50%, about 50% of the total bridge inventory, due to, and also the reinforced concrete structures are cheap, right? But it also comes with a cost in the service life maintenance issue when it comes from the bridge repair, rehabilitation due to corrosion. And that price tag is also significant. For example, a recent study comes with a $13.6 billion can be attributed to maintenance costs for the entire industry. And also if you consider with the life cost, cycle cost, the increased factor can be up to 10%. So the maintenance is not cheap, and it's kind of a headache in the DOT personnel. So how do we address this issue? So this was part of my PhD dissertation back in the last decades when I was doing my PhD study at Florida International University. This is as part of a multi-university research grant from NSF, led by University of Nevada, Reno, Dr. Saidi's group. And what we did is that this is the first generation of the CFFT, which was mentioned in the second previous slide, of using the concrete filled FRP tube, and this is our component at FIU to conduct a large-scale column and column band test using this type of configurations, and then the cyclic behavior shows it's a very promising application, and then it was incorporated into a four-span bridge test, large-scale bridge test on the shake tables at the University of Nevada, Reno. So both tests were published in 2009 and 2013. So this was the kind of the first generation of the new concept of CFFT, and this shows a lot of strength increase. However, the water can still intrude through the joints, right? We talked about axillary bridge construction. And when you use axillary bridge constructions, you want to prefabricate and assemble all together. So that will introduce the joints. Right now, the joints are super difficult to construct and to prevent future maintenance issues by water corrosions. So this is a second generation of the ideas of how to promote the application of FRP material together with the UHPC material. So we are replacing the reinforced concrete by the UHPC together with stainless steel. Now, the FRP shell will act as the first guard against the water and chloride intrusion, and the UHPC core also boasts a much higher resistance to corrosion due to the impermeability than the conventional concrete. And of course, the stainless steel reinforcement does not typically corrode on normal situations. So the whole configuration can definitely can resist the corrosion problem, and as such to significantly reduce the maintenance cost in the future DOT and maintenance problems later on. So the materials here, we have three constitutional materials. First of the FRP shell. Down the left bottom was the test that I did where we did in the FIU. So this was the most advanced behavior with an off-the-shelf filament wound off-the-shelf product, glass FRP tube, and this exhibits the largest seismic performance. And out of the other four types of, or different types of FRP using glass FRP or hybrid or carbon FRP. So we have the strength here, 10.3 KSI in tensile strength or 23 KSI in flexural strength, and the tube thickness is 0.22 inch, and the outside diameter is around 12 inch. And the UHPC core was the property was provided by Yilei, Bill Coolidge, the president. Provided the material specifications, and also answered a lot of questions from my group. That's kudos to him. And this is the material capacities and everything that was provided by Yilei. We used 27 KSI and 2% of steel fibers in the simulation. All right, and then comes to the stainless steel reinforcement. So we have investigated at 1.5 typical. This is a typical reinforcement ratio for a concrete structure for columns. And for stainless steel, it's normally provided by the grade 75 with 75 KSI yielding strength. And here to the right, there is a reference from Lolini in 2018 published in Corrosion Reviews. It shows all the infrastructure projects, especially the bridges around the world. So according to the chronological sequence, the first application most likely is in 1984, 3 decades ago, and up to the most recent one for example, the light transit, rail transit in Edmonton, Alberta. Okay. All right, so how do we do that? So this is simulated using a OpenSees. OpenSees was developed by UC Berkeley 2 decades ago, and is still widely used in the earthquake engineering community. And we tested 4 columns. Note that 2 columns was from my previous study, and which is using the reinforced concrete. I'll touch about that later on. So the column was using the regular reinforcement or UHPC and with FRP tube. So both were simulated using a 7-section column model under either cyclic test on the top or at ground motions, which I'll talk at the end. So the columns were tested under displacement control from 0.5 inch to 3 inches, which is not toward the failure. And the slippage was neglected, and the connection was assumed to be perfectly fixed. So 4 specimens. So here for the illustrations, we have a concrete column with a core and a reinforcement. So the 4 specimens were configured whether we have or without FRP shell. and whether we are utilizing UHPC core or regular reinforced concrete core, or whether we're using the conventional steel reinforcement, grade 60 steel reinforcement, or grade 75 stainless steel reinforcement. So we come up with the two conventional specimen with designated by RCCS, reinforced concrete, with strengthened with conventional steel, and then we replace the reinforced concrete just simply by UHPC and with stainless steel. And then a previous study, we come up with the FRP2 to confine the reinforced concrete, and then finally we replace the reinforced concrete by UHPC. So the 4 specimens. So here are the results. We can see the cyclic behavior of the first one is the regular reinforced concrete. The red one is the regular reinforced concrete. The maximum force response at cycle 6 is 10.9 versus if we include the FRP tube, then we have 104% of increase, 2 times of the original at cycle 6. Now, in terms of UHPC, if we use UHPC and stainless steel without FRP tube, it's 12.5%. And if we include the FRP tube, it comes to 26%. So now you can see that in both FRP, including of the FRP material for both reinforced concrete or for UHPC, the increase is a lot. 100%, almost more than 100% of the increase. Now, when we compare all 4 specimens altogether, you can see that the increase, when we compare the increase from, so this is a control specimen, right, reinforced concrete, the regular reinforced concrete specimens. If we replace reinforced concrete by UHPC materials, we have only 14%, and I'll explain that in a minute. And then if we include the FRP tube, the increase from the regular reinforced concrete was 104%. Note that these 2 specimens, FRP RCCS as well as RCCS, those 2 results were validated by previous experimental results, which means that this the whole analytical study was validated by the experiments. Now, if we include the FRP tube around this UHPC, now it's compared with the regular reinforcement, it's 138% of increase. So here to the right, you can see a clear picture of how the response envelope for all the 4 cases, and also including the cumulative energy dissipated which all shows a superior behavior of the new proposed system. Okay, so the results from the 4 subcyclic tests, the overall performance of the new configurations definitely has the best cyclic performance in initial stiffness, flexural strength, and energy dissipation among all 4 columns, and of course the effect of including of FRP shell for both the UHPC specimens or regular reinforced concrete specimens were superior in terms of 108% or 104%. At all times, it doubled the original performance. And now here comes the whether we are using UHPC or not, right? Because we see that the increase is only 17% and 14%, and this is attributed to the fact that this column is a flexural control specimen. So flexural control specimen is contributed by FRP tube in flexure. If the columns were more compression controlled, and that would definitely lead to a significant increase of the UHPC versus the regular reinforcement. So the increase of the UHPC shell, the increase using the UHPC versus the conventional reinforced concrete is 17% and 14%, right? So this 17% and 14% part of that is coming from, the increase of the stainless reinforcement grade, which is 75 KSI versus conventional steel, yielding strength at 60 KSI. And albeit we had the reinforcement has increased, but you can still see the increase of UHPC to regular reinforced concrete, which I didn't cover here, calculated at about 5% to 9% of the increase, if we keep the reinforcement grade at the same time. Okay? All right, so it gives us a confidence about using this new proposed, with new proposed systems, and a parametric studies was carried out by using varying the FRP FRP ratio, and we under the same UHPC coordinate reinforcement under 4 cases. So this will lead to a analysis by using the obviously higher FRP ratio will lead to a higher capacity. For example, it leads to 55% of increase from the larger to the second, and then the second parametric study was carried out by using simply varying the reinforcement ratio, and this is carried out by only stainless steel materials by using 1.5% of grade 60 and 3% of grade 75 in 4 cases. And obviously, you see that the higher reinforcement ratio will definitely lead to a higher capacity. So with that, finally, this model was carried out using ground motion analysis, time history analysis under 3 earthquakes. The most current one is in Turkey, 7.8 magnitude Turkish earthquake, and also a Tabas earthquake and a Soma earthquake, and the results are here. So in both cases, in all 3 ground motion analyses for displacement, so base shear and column top displacement for the new proposed systems were all significantly reduced with the previous analysis. So notice that these 2 displacements were studied with the FRP tube, using UHPC and using the FRP tube with the regular reinforcement. Okay, so final conclusions. The corrosion-free member has the highest performance in all categories of seismic performance. The enhanced fracture capacity is mainly due to FRP, and then the compressive contribution of UHPC will be more for the compressive controlled members. The parametric study shows that both FRP and steel reinforcement will have a significant increase, but you still need to optimize the whole situation by using more rigorous analysis, using parametric studies, and also the experimental results. The ground motion study finally reveals that the whole system was superior also in the earthquake ground motion time history analysis. Thank you.